Linear programming is the use of the systems to actually analyze and see what's happening. And this is where what we were doing with the systems is going to go into the next step of telling us something, not just finding out where they intersect, but helping us see a bigger picture in business or in medicine or in something else. So we're going to start with some basics, and we're just going to go through, and I passed out this morning the foldable. This is how the foldable is going to be set up. Your vocabulary is the first tab, then the feasible, then testing, then maximum minimums, then using linear, and application. So go ahead and set up your foldable like this. Throughout this video, I'm going to have several times where I'm going to get you to pause it. I'm going to tell you to pause the screen so you can record the vocabulary. So the first couple of vocabulary, your constraint, are the inequalities that kind of set up your border region. They set up your feasible region, and that gets the problem at hand. Linear programming is just the method used to find the maximum minimum value with your system of constraints. And when I ask you for the feasible region, that's just the shaded region created by the inequalities. And it's basically that shape where all the constraints meet or are satisfied. Go ahead and pause it right now so that you can write down these problems. The next 4 vocabulary words, your objective function is a function with the 2 variables that give you your maximum minimum. It's going to be like your profit or your cost or whatever you're trying to either maximize or minimize. And you're going to plug each of your variables into this for your vertices to help come up with making your decision of which one is what is the maximum or minimum amount. When I say the bounded region, is that polygon where all the maximum minimum values exist. And an unbounded is where there is no maximum minimum dependency. The feasible region cannot create a polygon. We're not going to go into the unbounded right now. That is something for later. But for right now, we're going to be just dealing with bounded regions. But I just wanted you to be aware that there are such a thing as unbounded. And the vertex principle of the linear program, this is the reason linear programming works, as there exists a point in each of the objective functions where one of the vertices is in the feasible region. Again, I want you to write those vocabulary words down. I'm going to pause the screen now, and then we'll pick up with drawing out what these look like. So we're going to go ahead and just look at what these vocabulary represent. The C is your objective function. It's your cost function that you're going to be plugging all the vertices back into. Those little blue dots are your vertices. That green that's marked is your feasible region, and the pinks are your constraints. So for sketching your feasible region, is going to convert your constraints into slope-intercept is what I recommend. You can also use point slope or find 2 points or find the 2 intercepts and plot it. So basically what I'm saying here is I need you to graph. We need to get it into a graphable method. So we need it to be ready to graph so that you can graph it on the next step. And then we're going to look at shading it. We're going to look and see all of them combined, where would the shading region be? And if it is a region, we're going to look and see where all those regions overlap, and that gives us our polygon that we're going to use. Again, pause your screen if you need to have a little more time to write these down. Let's take an example of this. So in these, you're going to have constant functions, because they usually are going to create our walls. And then you're going to have some that are going to be like your normal linear. So let's go ahead and look at the constants. So if it's x that's when they're going to be, the lines are going to be vertical. And so we think about those border walls. So if it says 0 is less than x, and so we're going to have this line of x equals 0, you're going to graph. And then you're also going to have the line of x equals 5. And so those are your two walls. They are both solid because there's that bar underneath. Then the other constraint we have is our y is greater than 0. And this is going to be horizontal anytime it's y equals. And so we're going to do a horizontal line of y equals 0, which is just your x-axis. And so we can kind of see what this means. That first two says that we are between those two, and if we're greater than y, that means we shade that way. Now let's take our three equations beneath it. The first one, x plus y is less than or equal to 7. And then solve it for y, negative x plus 7. So that tells me my y-intercept is 0, 7. And then my slope is negative 1 over 1. And then I fall down 1, go over 1. Fall down 1, go over 1. I'll go ahead and color that black so that you can see that it matches that equation. Okay, my next one is going to be this x plus 2y is greater than or equal to 4. Get the x over to the other side. And then divide both sides by 2. I usually do the y slope-intercept form just because it's easier for me. But sometimes other situations will make other equations easier. So it's just like what you were doing in the math yesterday, but we're going to take and go into some of these other equations. And then my slope, my y-intercept was 2. My slope was fall 1 over 2, fall 1 over 2. I'll keep doing that to go off my page. And as you see here, they don't always have to meet up. And so grabbing that blue line in there. So now let's go to our last one, which is our y is less than or equal to x plus 5. So that's already done for us. So that's 2, 4, 5, and then move up 1 over 1. And so we now have our regions graphed. Oh, I should have done that in a different color. Let's go back and make that green. Okay. So we now have that region created. And so we got to figure out where would it shade. So I need to shade below that green line, below the black line, above the blue line. So that's going to create this region here. We've already talked about where the red lines shade. And so that's our feasible region, that polygon there. So testing your vertices, you're going to actually go through the same steps we've just done. We're just going to add in some steps. You're going to identify what those vertices are, and you may have to use a system of equations to help you find those intersecting points, and then test your vertices into the objective function. So let's see what that looks like. So this is example 2. I'm going to go ahead and get you to go ahead and graph each of those graphs, and then the next slide I'll show you what they look like when they're graphed. So you should have had that blue region have a slope of -1/2, so it looks like this. Your black one should have had a slope of -1, and it should be dashed. And then your red, which was your x is greater than 0, and your green, which was y is greater than 0. So now the next step is we need to identify what each of those vertices are. And so the importance that are important are each of these vertices. So we have 4 vertices that are important. This first one, which was at 0, 1, 2, 3, 4. The next one, which is at 4, 2. The next one, which is at 6, 0. And our last one, which was at 0, 0. Now we're going to plug these into your objective function. So our objective function said that 3x plus y is what we're plugging it into. And so that means we have 3 times our x value plus y. So 3 times 0 plus y, which was 4 in this case, means that objective is going to be 4. So 3 times 4 plus 2, 12 plus 2 is 14. And the good thing to remember on this one is I can't actually be at 14, so it's going to be actually a little bit less than 14, but it can't actually be 14. And then our next one, which was 3 times 6 plus 0, so 18 plus 0 is 18. And again, we can't actually be at 18, so we're going to be a little bit less than 18. And then our 0, 0. So 3 times 0 plus 0, 0. So we're going to maximize at that order pair of 6, 0. And so when we're trying to find that maximum minimum, you're actually just going to be doing the exact same thing we did and just identify your largest value. I want you to try to do this one, setting it up and identifying your shapes on your own. So I'm going to give you a second to get that actually plugged in. You should have come up with your feasible region looking like this. And let's go ahead and identify our order pairs. So this one doesn't matter. These are the vertices that matter. And you just start at 1 and keep going around. So I'm just going to start at this one and work around clockwise. And so that is 0, 2. And we're going to be plugging these into the function n is equal to 100x plus 40y. And the next one is going to be 0, 4, then 5, 1, and then we have 6, 3, and then we have 0, 5, and the last one we have is, oh, not 0, 5, sorry, I said that backwards, 5, 0. And the last one we have is 3, 0. And so we're going to be plugging those in. So 100 times 0 plus 40 times 2 gives us 80. And the ones that we have that are dashed are the second, the third, and the, or excuse me, second and third ones. So these are the two that are dashed. That means we'll be close to, but not exact. So 100 times 0 plus 40 times 4 gives us 160. 100 times 5 plus 40 times 1 gives me 540. 100 times 6 plus 40 times 3 gives me 600 plus 120, 720. And then we have 100 times 5 plus 40 times 0, giving us 500. We have 100 times 3 plus 40 times 0, giving us 300. And so that means that this is our maximized function. So the baker earns 15 cents profit per glazed donut and 40 cents profit for a jelly donut. And we want to know, he wants to buy no more than a dozen donuts and wants to try one of each kind. What is the maximum profit the baker could earn? So let's go ahead and write out our constraints. So let's start off with our profit equation. To me, that's always the easiest. And we could think of this 15 cents as 0.15, or we could think about it only in cents and just realize we're talking about cents, not dollars. And so that's the way I'm going to go about it. And so for our profit, we're going to get 15 cents for every glazed donut plus 40 cents for every jelly donut. And so that's as simple as the profit equation is. We've already taken care of that. Now, the customer wants to buy no more than a dozen donuts. A dozen is 12. So no more than means we want to buy less than, but we could also buy 12. So glazed plus jelly is less than or equal to 12. And the person wants to buy at least one of each kind. So that means that glazed is greater than or equal to 1, and jelly is greater than or equal to 1. And then we're going to choose our axes. I think this is the way I chose. And plug those in. Oops. And then we're going to graph our points. And so I'm going to go ahead and pause it while you get these graphed. And then we'll meet back on the next slide where we will go ahead and find our constraints and then test. Okay, so we plugged it in. We got our feasible region. And now we're going to take and find our profits. Well, in this case, and I went ahead and counted by twos because my graph was relatively small. And so this is the point of 1, 11. And this is the point of 11, 1. And this is the point of 1, 1. And so I'm going to go ahead and test those. 1, 1, 1, 11, and 11, comma 1. And so we're plugging in 15 times 1 plus 40 times 1 equals 55. And then we're going to do the next one, 15 times 1 plus 40 times 11. So that's 440 plus 15 is going to give me 455. And then we have 15 times 11, which that is 165, plus 40 times 1. So 165 plus 40 is going to be 205. So my maximum profit is going to be $4.55 if they order one glazed and 11 jelly. So let's go ahead and I'm going to get you to do this one all on your own. You can work with your partner at your table if you would like and see if you can come up with the equation. And then once you do, I'm going to have it on the next slide so you can see if it actually matches. So go ahead and pause now and work at your table to come up with this one. So on this one, you should have come up with your equations being your profit equation of 12x plus 20y because it takes 4 hours for a small and 6 hours for, because it costs $12 for every small and $20 for every large. He has a minimum amount of time he has available, which is 60 hours. So 4x plus 6y is less than or equal to 60. He's going to have to spend at least time can't be negative, and he's going to have at least 0 of the large wagons, but he wants to have at least 6 small wagons. So what can he do to maximize his profit? And when you do this, you see that his maximized profit is going to be 6 small and 6 large.